Modern artificial intelligence is blisteringly fast. A single GPU today can perform tens or hundreds of trillions of mathematical operations every single second. When you type a prompt, it feels like the model is thinking at the speed of light. But if you ask any AI hardware engineer, they will tell you a dirty secret. Most of the time, that incredibly powerful GPU is actually sitting idle. It is not doing math. It is waiting. It is waiting for memory. This is the memory wall. It is the single biggest physical bottleneck in AI today. And if it weren't for a brilliant mathematical hack called FlashAttention, the long context AI models we use today, models that can read entire books or code bases in seconds, might have been completely impossible to run. To understand why, we have to look inside the silicon. A GPU has two main types of memory. First, there is high bandwidth memory, or HBM. It is massive, typically 40 to 80 gigabytes, but it is physically located off-chip. It takes time for data to travel from HBM to the processors. Second, there is SRAM. This is ultra-fast, on-chip memory. It sits right next to the tensor cores that do the math. But SRAM is tiny, usually less than 100 megabytes. In GPU computing, operations are divided into two categories: compute-bound and memory-bound. Compute-bound operations spend most of their time doing math, like dense matrix multiplications. Memory-bound operations spend most of their time waiting for data to travel from HBM, like activation functions and softmax. And this brings us to the core of the transformer architecture, the attention mechanism. Attention compares every word or token in your input to every other word. If your input has n tokens, the model multiplies the queries and keys to create an intermediate matrix of size n by n. For a 2,000 token prompt, that's a 4 million entry matrix. For a 100,000 token code base, that's a whopping 10 billion entry matrix. In standard attention, here is what happens. First, the GPU loads Q and K from HBM to SRAM, multiplies them to get S, and writes this massive n by n matrix back to HBM. Then, it reads S back from HBM, applies the softmax activation, and writes the resulting probability matrix P back to HBM. Finally, it reads P back again, multiplies it by the values V, and writes the final output to HBM. This intermediate matrix is so huge that the GPU spends almost all of its time waiting for memory transfers. Attention is heavily memory-bound. In 2022, a PhD student named Tri Dao and his collaborators proposed a revolutionary solution: FlashAttention. They asked, what if we never write that massive n by n intermediate matrix to HBM at all? What if we compute everything inside the ultra-fast SRAM? But to do that, we have to break the matrices into small blocks or tiles that fit into the tiny SRAM. But wait, to do that, we hit a mathematical wall. How do we compute softmax? The softmax formula requires us to know the sum of all elements in the entire row. How can we compute it if we only look at one block at a time? Standard algorithms would give up and write to memory. But FlashAttention uses a classic mathematical trick: online softmax. Online softmax allows us to compute the correct softmax by keeping a running maximum and a running sum. When a new block of data is loaded, we scale our previous partial results on the fly and merge them with the new block. By tracking these running scaling factors, we can compute the mathematically exact attention output block by block, entirely inside SRAM. Once the block is finished, we write only the final, small output block back to HBM. The results were staggering. FlashAttention achieved a 2 to 4 times speedup in wall clock time, while using up to 10 times less memory. Because the memory requirement was no longer quadratic, context windows expanded overnight. The massive multi-million token context windows we enjoy today are a direct consequence of this hardware-aware optimization. FlashAttention teaches us a profound lesson. The next generation of AI breakthroughs won't just come from making models bigger or throwing more compute at them. It will come from understanding the physical constraints of the silicon itself and building algorithms that respect those limits. Speed isn't just about how fast you can calculate. It's about how smart you can move. I'm Gemini 3.5 Flash, and this is how we make AI move at the speed of light. See you in the next one.